So we've done a section of this unit which was applications of derivatives to curve sketching, and now we're going to do a bunch of other applications to derivatives. Thank you. And we're going to start with kinematics. You have an extra page. You have, oh, you have more sinusoidal functions. I think we just drew that but didn't, we're going to skip that one. We'll go to kinematics. Because we had, I think I put it on the video and I said, here it is, it's a calculator one. This is what it would look like. Everybody ready? No, of course not. It's been 25 years since school's been canceled. What do you think? No? It's not canceled yet. They canceled buses already. But it's supposed to be bad Wednesday and Thursday. Yeah, I think they're not going to have school on Friday, for sure. Yeah. But. It might be tomorrow. We'll find out. So, a little review. What does the derivative tell us? It tells us the slope of the tangent at a certain point. That is, slope is your change in your y values over your change in your x values. Okay? The derivative represents the rate of change with respect to x. So now if you had an equation that was, and they use s for displacement, I guess because the third letter is s. Okay? Or distance, because I think d is for distance and displacement, gets a little bit confusing. So s equals, if you had some equation, here we'll go. Suppose you had some equation that was displacement, okay? If you found the derivative, and we wrote the derivative in terms of s and t and used Leibniz notation, do you see that ds dt would be negative 10t plus 1? Okay? Now, if s is distance and t is time, what unit do you measure that changes distance over change time? Speed. Speed or velocity, right? If you want to say how fast are you going, 5 kilometers per hour, it's a distance over a time. And so the derivative of any equation that measures displacement is going to be velocity. And then the double derivative is going to be acceleration. So I modeled a question of throwing a rock up in the air with an initial speed of 1 meter per second. Okay? What does the second derivative come out to be? It's the acceleration. It should be negative 9.8, but you would have often seen in application questions in grade 11 math starting with negative 5. because they didn't want you to work with decimals, and then they could create questions that factored nicely. I mean, -10 for an acceleration is close, if you're rounding, but not perfect. So we start to see some of the numbers that existed in grade 11 math and a reason for them. I said I threw it up with an initial velocity of 1 meter per second. An initial velocity would be at time 0. So my derivative equation here, I could plug a 0 into it, and I could see that I would get 1. And so I can find an initial velocity by just finding my derivative. So what's going to happen is a lot of the stuff that you've studied in physics is sort of going to get simplified into analyzing it with calculus. Now, if you were looking for an average speed or average velocity, and we'll talk about the difference between velocity and speed, you would take the slope of a secant line between 2 points. If you want to find an instantaneous velocity, you would find the slope of your tangent. So we've seen instantaneous and average rates of change before. We're going to see them in kinematics as well. So what's the difference between velocity and speed? Velocity is a vector. It has a direction. Speed is just how fast you're going. So when we talk about acceleration, we talk about -9.8 because it's coming down. So when I throw an object up in the air, it would have an initial speed that's positive, eventually stop, and then have a initial velocity that's positive. It would stop, and then as it's coming down, we would say its velocity is negative because it's changed its direction. But if we said how fast is it going, we'd always use positive numbers. And for the most part in calculus, the kinematics questions are fairly straightforward. So you get an equation for displacement. S equals t squared plus 3t. If you want to find the average velocity over 1 to 3, okay? Well, at t equals 1, S would equal 4, and this is in meters, 4 meters. And at t equals 3, 9 plus 9, S would be 18 meters. Can you see in those 2 seconds you have changed 14 meters? So your average velocity would be, well, we've changed 14 meters in 2 seconds. 14 divided by 2. Your average velocity was 7 meters per second. But if you want to find the instantaneous velocity at any point, that's where you would take your derivative. So ds dt is going to equal your velocity. In this case, it would be 2t plus 3. And from that, we can answer questions like, what's the initial velocity? Anytime it's asking for an initial, that's when time is 0. What's the velocity after 4 seconds? Just plug 4 into your velocity formula. And we get 11 meters per second. Probably the biggest thing in kinematics question is checking, do you understand that the derivative of displacement is velocity, and later on that the derivative of velocity is acceleration. So if we want to find the velocity, we would have to find the derivative of its displacement. This one has an even more accurate acceleration built into it. After 2 seconds, we get negative 19.6 meters per second. One of the things that you'll have to interpret while working with these questions with kinematics is which equation they want you to use. Okay? So if I need the stone's velocity, I have to find the derivative to get the velocity formula. If I want to find the time when the stone will hit the ground, I know that the height then, oh, it is. It is in the function. It's not expressly stated. If you dropped it off from the cliff, there's your stone, blue square stone, because that's very accurate, is dropped off from the cliff, its height is going to be, when time is 0, does it make sense that the height of this cliff is 122.5 meters? It got a little smushed. It then lands on the ground. We need to find the time, so we need to solve for t. What do we know about it when it hits the ground? Well, the velocity is 0, but that's because of the impact. I don't think that'll show up in the equation, though. Does it make sense that you would use the original equation and put the height to be 0? And then we just need to solve this. Does anyone know what 122.5 divided by 4.9 is? 25? Oh, that is a nice number. I probably planned it that way. And then, when you square root, normally when you square root both sides, what do you have to do? Plus or minus, right? Why in this case? It's like, oh yeah, before I dropped it, it hit the ground. I just didn't tell you.
It hit the ground 5 seconds ago and 5 seconds from now.
Yep. So we only need the positive value here. how fast is it going when it hits the ground, okay? This is the important math to do before you tell your friend who's at the bottom of the cliff, hey, I think you should catch this stone. I'm going to drop it off the cliff. Well, let's just see how fast that stone would be going if your friend was there. So now we can, I guess, we can add to the artwork. This is you. And then we'll imagine your friend in a second. So it takes 5 seconds. We've got our formula for velocity. Velocity was negative 9.8 t in this situation. We plug in 5 seconds, and our velocity is negative 49. Is that right? Meters per second. Okay? That's decently fast, right? You imagine a vehicle traveling. Well, we'd have to figure out how much this is in kilometers per hour, but this is pretty fast, right? Imagine deciding to stand at the finish line in the 100-meter sprint, and Usain Bolt runs into you. How that would feel. Okay, how fast is he traveling? 100 meters in about 10 seconds. So about 10 meters per second. So this would be about 5 times as fast as that. Okay? So right? Not a good idea for your friend to maybe try to catch that stone. Yeah, that's pretty high. Hey, catch. Okay, games not to play. Yeah, that's all, yeah. This is all about trying to get views on social media. These questions, that's how they were designed, and that was the reason behind them. So your acceleration is your derivative of your velocity. So it's equal to the second derivative of your displacement, which is in the next line anyways. So that's your instantaneous acceleration. And you'll notice in most gravity questions, it's gravity. I know. So we have some object. Its displacement is given by this function. So again, the key thing in understanding a kinematics question is, which equation should I use to figure this out? Question 1 is asking velocity. Chances are you want to use your velocity equation, which we don't have, but we can find by taking the derivative of displacement with respect to time. That would give us 3t squared minus 24t plus 45. At t equals 1, then, velocity would equal 24, and what are units? Meters per second. What does it mean for a particle to be at rest? It's not moving. If something's not moving, what is it telling you? It has no speed, it has no velocity. So that particle at rest is telling you the velocity is 0. If the velocity is 0, we have our velocity equation. We could plug in 0 for our velocity. I have a common factor of 3 here that I'm going to take out. This question factors nicely. Don't have to use a quadratic formula. Make sure I include my units, so at 5 seconds and 3 seconds. It is at rest. Well, I put the statement because you could have included the units here, but I just wanted to make sure that we included the units. I would have accepted if you put a little seconds by the t equals 5 and t equals 3. I'd be fine with that. Motion diagram. This is something that is in your textbook. It is, for those of you who've done IB math, you never heard of a motion diagram. It's basically the same thing as graphing, except you make a number line and you put key points on your number line. So what do we know? That this object at t equals 0, so important points, at time equals 0, it's going to start at 7 meters. Okay? And a little thing about our derivative, and again, a motion diagram is very similar to graphing. So if we're graphing its displacement and its motion as it travels, when you were graphing and sketching a graph, you'd be like, oh, here's my derivative. It's equal to 0 at 3 and 5. If I plug in a number less than 3, like 2, this would be negative. This would be also negative. Negative times negative is positive. It's going to be increasing till 3. Then I plug in 4, and this one's still negative, but this one's positive. So then it decreases, and then plug in something higher. Both of those would be positive. It's increasing again. So our motion diagram is sort of like imagining something moving horizontally. It's going to be increasing until it gets to 3, then decreasing until it gets to 5, and then increasing after that. So on our motion diagram, we have a starting point at t equals 0. S was equal to 7 meters. At t equals 3, we could plug that into our equation, and S would equal, how are you going to put all those things back on your pencil? Oh. So quickly going to plug this in. 27 minus 108. Oh my goodness. It's 61 meters, thank you. And then at t equals 5, sorry, 57 meters. So 10, 20, 30. Looks like this would be about 61 meters there, 57 meters there, roughly to scale. The motion diagram is going to look like this. My particle is moving this way, increasing until it gets to t equals 3. It then comes back and changes direction till t equals 5, and then continues that way afterwards. Similar to a graph, you still have like maxes and mins, but it's sideways. So it's just a different way of imagining something. But here, when you have velocities being positive and negative, that means it's changing directions. So we're thinking of it horizontally. It's going forward, then it comes backwards, then it goes forward again. You could graph it normally and then have it as, it's exactly the same, like your graph, 1, 2, 3, 4, 5, it would have there's your graph. Yeah, it's like turning your page. But a motion diagram puts the times on there, and it's not, a graph spaces things out correctly. A motion diagram just labels, here's when it's 3, here's when it's 5, just when it changes direction. Whereas a graph can be wider and narrower depending on the time. All right, so there's something a little bit new, not that exciting. Continuing on, we want to find the acceleration after 1 second. So the acceleration will be the derivative of velocity, or we can write that as the second derivative of displacement. We found our derivative to be 3t squared minus 24t. So our acceleration formula is 6t minus 24. When is the acceleration 0? Move it over. At 4 seconds. Oh, and we didn't find it after 1 second. At t equals 1, the acceleration would equal negative 18 meters per second squared. What does that tell us about it? It's accelerating, but what does that negative acceleration mean? Yeah, it's just accelerating in the direction that's not defined as positive. But in our motion diagram, right, pretend I'm a little particle. What am I? Like, I'm not going backwards. I'm accelerating backwards, which means I'm slowing down. Slowing down in the direction I'm going. You're speeding up in the, yeah. Like when you have, in this case, at 4 seconds, if we look at our motion diagram, okay, it makes sense that here it's at rest, and here it's at rest. In order for it to get to at rest, it would have to be slowing down, right? Then at 4 seconds, which is somewhere in here, would have been an inflection point on our graph. At 4 seconds, it's switching from slowing down, slowing down, slowing down, slowing down, and picking up speed in this direction, and then now it's slowing down in this direction and picking up speed to go in that direction. Maybe we can. There you go. Just for you, Michael. Okay, here's one for you to try. Oh. And I should include my units here so I don't lose marks. There we go. 3 seconds and 1 second. Good? Did I have?
The number line show that it's increasing before and decreasing after to show that they're proper mins and maxes?
It just asks that they're at rest. So the only, like, it could even be a stationary point of inflection. It's still at rest at that moment. So all we're doing is saying my velocity is 0. It doesn't need to be a max or a min or changing direction. Because technically, if I'm an object, I can stop and then go again without changing direction.
You can't. That's not allowed.
Oh, sorry.
I have the physics tools to rescue.
Finding S at these times, so this is just a matter of plugging in the 3 and the 1 into the displacement. So again, that was a scary laugh. To keep you safe, I will shut the door. And then your motion diagram, starting t equals 1, t equals 3, and then it keeps on going. Question? Yes, we know that it keeps going to the right, because otherwise it would have to change direction again, and you would have another moment that it would be at rest. But from the, yeah, you can tell it's an x cube graph and just like, oh yeah, right? So you just turn your head sideways, and then you can see. And finally, how did you do on the acceleration? Found your acceleration formula, plugged it in,